TEL's market-leading airflow controls and monitors are used across the world to improve safety, reduce costs, and save energy in thousands of laboratories and industrial environments. Our products are designed to complement one another and work together to give end users complete environment control. The AFA 5000 laboratory room space controller can be used to reduce energy consumption and maintain air quality and comfort levels in any type of room space with mechanical ventilation. TEL's pioneering AFA 4000 airflow controlling and monitoring system has been developed specifically to reduce the energy usage and costs associated with running a laboratory, consequently shrinking its carbon footprint. Our auto sash controller for fume hoods maximizes energy savings and provides increased safety for operators by closing the sash automatically when the operator isn't present in front of the fume hood. TEL's AFA 1000 bleed controller is a wall-mounted fresh air bleed controller that controls the VAV system duct pressure using a fresh air bleed damper or fan inverter drive. Working together, these products provide a complete VAV system for laboratory environments. Fitting TEL's VAV control system to your fume hoods and air supply system can typically reduce your energy costs by up to 85%.
Paul and Bill, the show is yours.
Thank you, Tim, and welcome everyone. Appreciate you joining us today. We are going to be speaking about energy conservation opportunities within university lab buildings. My name is Paul Zasada, and I am the president of the ECM Holding Group. And I have with me today, Mr. Bill Herrera, my colleague and friend. You know, Bill and I joined ECM 8 or 9 years ago, and we were tasked with building the energy business in developing offering within the laboratory systems. And we are, in that 8 or 9 years, we have seen, we've been in hundreds and hundreds of labs, and we have developed dozens of projects within the lab space. And today, what we plan to do is share some of our stories and our experiences with you all. So up here is our agenda for the day. First, we're going to talk about why labs are such high energy consumers, often the most energy intensive buildings on campus. We're going to discuss some of the key design codes and operational health and safety requirements for working in labs and operating labs, and some of the changes that we've seen in the code and design practices in labs that have created some excellent opportunities for energy efficiency retrofits. Then we're going to dive into what do you actually do in a lab to generate energy savings. And then we'll jump out of the lab space and we'll talk about the exhaust fans and how new technology has provided opportunities to utilize VFDs on exhaust fans where just a short time ago, they were not available to do so. So let's dive in. Why are labs such high energy consumers? Labs are very exhaust intensive. There's a great deal of equipment in labs that are designed to exhaust fumes from chemicals. The purpose is to keep the lab users safe. We've got fume hoods, biosafety cabinets, and just general exhaust in the lab space that's going that, this is not return air. This is exhaust air that's coming from the lab going through the exhaust system and being exhausted up through the roof of the building and out of the building. Now, this air needs to be replaced with outdoor air. So, in an efficient building, every 10 minutes you're changing the lab air out every 10 minutes with new 100% outdoor air that needs to be heated and cooled and sometimes dehumidified as well. And that's for an efficient lab. Inefficient labs, every 2 minutes you're changing out the air in that lab with 100% outdoor air that you need to heat, cool, and dehumidify. So in essence, these are once through systems. I mean, air's coming into that lab and going right out through the roof and into the atmosphere. So it's extremely expensive to operate these labs, even when they're running efficiently. But when they're running a little bit wild, they can really get out of control. When it comes to lab designs, engineers by nature are a little bit conservative. I am one. And in a lot of the designs, when they're set up, were conservative in nature. So the labs have been over ventilated. So we see this quite a bit where a lab is well beyond where it needs to be just from the get-go, from the design engineer start date, particularly in labs that are 10 years old or more. And back in the day, there was really only one or two major players in the lab control system industry, and they were pretty proprietary. They weren't giving you visibility into the lab's operating system. The facility staff didn't have availability or the ability to maintain those systems. The maintenance agreements were expensive, so there wasn't a lot of ability for the university themselves to work on it. It would be one of the first things that would be cut from the budget is maintenance for this. And, to some degree, there was a perceived risk of working in labs, a liability. So people were kind of scared. So they just kind of took a hands-off approach. And what that led to was just systems starting to run wild. Nobody's really paying attention. And when there's such, energy intensive systems, these once through systems, if you're not minding the store, you're going to start getting very inefficient and it's going to start costing you dollars, which creates a great opportunity to get in there and perform an energy performance contract. This picture over to the right, this is a university in Massachusetts. This is 100% outdoor air, makeup air unit. You can see we've got the exhaust fans built right into the unit, and they have variable air volume capabilities. This is a fresh air bleed damper here. A VFD was supplied on the air handling unit, but they never set this up to operate properly. They had all the equipment to do it, but this lab, this number of labs has been running as a constant air volume lab, running full out for years and years and years. Even though the ability was there to be VAV, whether it was the design engineer, the original contractors, they never set it up to run that way. We find this all the time, that the capabilities there, but just nobody's either got the know-how or really wants to take it on to get things running efficiently. And that's where the performance contractors can come in and make some energy efficient modifications, and get great savings and a great payback. Now let's dive into some of the code issues around labs. There's multiple agencies that weigh in when it comes to design code and operating code for labs. ANSI Z 9.5 is probably the chief code, but ASHRAE dips in, so does NFPA 45. You've got a variety of state codes, depending on where you're working, that you need to think about. And these codes aren't written black and white, they're a little bit gray. So it generates this conservative nature when it comes to labs. Like I said, a lot of the designs are done conservatively, and there's a lot of waste, which creates opportunity. But when you really dive in, there's about 5 or 6 different things with the code that I want to summarize for you, give you a good feel for what's really important to pay attention to when you're retrofitting labs. First, it's about the fume hood. The fume hood is the most critical piece of equipment in a lab. That fume hood needs to be functioning properly all the time, or else you're putting the lab users at risk. And you need to maintain a face velocity across the sash opening at all times between a range, generally it's 80 and 120 feet per minute. Now this picture on the side here shows a lab user working inside a hood, and there's a sash opening here. And what we're talking about is making sure that the air velocity is flowing through that opening at a speed of generally 100 feet per minute is what the set point is, particularly at university. And the reason is that if you don't have good face velocity, there's a chance that anything someone's working on in the fume hood could come back out in the user space, and that would be a catastrophe. So it is super important that that face velocity is maintained at all times. And when you close the sash on a fume hood, there's another code requirement, and that's you can reduce the CFM, but you need to maintain 150 air changes per hour inside of that hood. And that's a recent change. It used to be more, and we'll hit that in a few minutes here. But that 150 air change per hour closed sash is a code requirement at a minimum. Now, also with your fume hoods, you are required to have a monitoring device that is measuring that face velocity across the opening. And should you fall out of an acceptable range, it needs to alarm, warning the user that that fume hood is no longer safe to use. You also need to certify your fume hoods on an annual basis that they are operating within these face velocity requirements, and that there's no cross straps in the room that could come in and create a hazardous environment. So that is required of all lab fume hoods once a year, and a report is generated annually for each one of the universities that, in most cases, it's generated that shows all the results of that testing. Now, moving on to the exhaust system, the exhaust stack needs to maintain a discharge velocity of at least 3,000 feet per minute. Now, the reason for this is you want to make sure that you're exhausting this plume at a high velocity and throwing it up and away from the building, away from any outdoor air intakes, away from anybody that may be working on the roof or thereby. So that requirement of just getting that plume up and away is one that's important to know, but there has been a few wrinkles in that recently, which we'll talk about as we go. And then it comes down to lab ventilation rates, turning the air over in the labs. The code's a little gray here. It's not prescriptive. It says it just needs to be sufficient to control exposure. And those air change per hour rates are key to energy savings, and you'll hear us talk about that quite a bit today. It also says that your contaminant should be controlled at the source. So it's a bad lab practice to leave chemicals out in a lab. They all should be stored in a ventilated storage unit, not in the fume hood. And when you do that, you have a safer lab, and your ventilation rates, are certainly allowed to be lowered. And lastly, it's about lab differential pressure. The code says that airflow needs to go from areas of lower risk to areas of higher risk. And what that means is, most labs are adjacent to a corridor, and you want air going from the corridor into the lab at all times. And the reason's pretty obvious. You don't want any chemicals, any smells that are in that lab get distributed throughout the building. And you need to monitor that differential pressure so that if it ever reverses and your labs are positively pressurized compared to the corridor, that it'll let the users know and immediate action can be taken. So that's not all the codes, but these are the ones that are really key when it comes to looking at working inside of laboratories. Now, over the years, there's been some changes, but before we do that, let's talk about air change per hour definitions. You're going to hear us talk a lot about air changes per hour, and it really is the key to energy savings. It's controlling air changes per hour. And the literal definition is how many times within an hour you're going to replace that lab air with 100% outdoor air. And to calculate the air change rate, you just take your lab volume and you use a multiplier, industry accepted, a 0.9 multiplier is used to account for solid objects in the lab like furniture and equipment that are taking up airspace. So you have your lab volume, and then you look at your exhaust CFM, you convert it to cubic feet per hour, and then you divide your exhaust cubic feet per hour by your lab volume, and that tells you how many times in an hour you're going to be turning over the air in that room. And that is a key term when it comes to running a safe lab and running an energy efficient lab. You know, the universities, I'd say 50% of them have an environmental health and safety officer that if you're looking at doing a performance contract in the lab buildings, you need to address them at the beginning, get them engaged. These environmental health and safety officers, they're the ones who are overseeing the code in the labs, the safety practices in the labs, and quite often they are setting the air change rates in those labs. So if you do get engaged at a university and there's an opportunity for a lab retrofit, you know, get the information for the safety officer. They're quite often your ally. They're really looking for opportunities to save energy in these labs. But the sooner you get them involved, the better chance you have them of being a part of your team and getting things approved and getting a project going forward. So now let's talk about some of the changes that have happened in the code and the design practices over the years that have created more opportunity to do energy efficient retrofits in the lab space. You know, ANSI Z 9.5, as I mentioned before, is probably the key code or the biggest code out there most people follow. And back in 2011, the closed sash ventilation rate was 325 air changes per hour. But in 2012, they changed it to 150 air changes per hour, meaning that you could reduce the amount of exhaust on your fume hood when the sash is closed by over 50%. That's a big change. And the next item isn't so much a code change as it is a design practice change or an industry standard change. As I mentioned, when it comes to ventilation rates, the code states that it shall be sufficient to control exposure. Well, that's pretty gray. It can be interpreted a lot of different ways. Oh, and 10, 12 years ago, most design engineers were designing to 12 air changes per hour around the clock. It was, you know, no occupied, unoccupied. It was just 12 air changes per hour or more. During the same time, Europe was much more progressive. They were in 6 air changes per hour occupied, 4 air changes per hour unoccupied. And we're doing that for years and years and years. Finally, you know, with the cost of energy being what it is and seeing the energy bills and what hogs these buildings were, the US followed their lead, and it became an acceptable design practice to have 6 air changes per hour in the lab when the lab is occupied, and 4 air changes per hour when the lab is unoccupied. And that was a big shift. So if you've got labs, even if they have an existing VAV control system in them, and they're over 10, 11 years old, chances are there's great opportunity to go in there and retrofit those with new controls and get your new air change rates. And it is a common and accepted practice to use occupancy sensors to do real-time unoccupied, occupied scheduling. So you're not just doing time of day scheduling, and there's significant energy savings to be had. Tim, can you please pull up our first poll question?
So here's our poll. And we will close the poll in 5, 4, 3, 2, 1. And the poll is closing. Get your last votes in. And we're closed.
So we've got 28% of the crowd is familiar with the code requirements, about 60% is not, and 14% says they are familiar with them, but they're not rule followers. So good feedback, thank you. So the majority aren't quite familiar with these, thanks. All right, so let's get into the meat and potatoes of the presentation. What do we do inside of laboratories to generate energy savings? So the lowest hanging fruit is really to convert from a constant air volume lab to a variable air volume lab. And to demonstrate this concept, I'm going to use this very simple diagram to talk about how variable air volume labs work compared to constant air volume labs. And this diagram is depicting a fume hood, and on the left is a constant air volume fume hood. And when the fume hood is being used and the sash is up, you've got 100% exhaust coming through that sash opening, going up the exhaust duct into the plenum and out the exhaust stack into the atmosphere. And you're maintaining your face velocity across that opening so the users are safe. On a constant air volume fume hood, when you close the sash, there's a bypass above the sash that opens up. So even though the sash is closed, you're still exhausting 100% of the air through that fume hood, up the exhaust duct and out the exhaust stack. So there's no change in exhaust volume on a constant air volume fume hood, as one would suspect. When you go to variable air volume, when the sash is up, you've got the same scenario as the constant air volume hood, that you've got 100% of the air coming through the sash opening, maintaining your face velocity and going up through the duct and out of the building. But when you close your sash, you're able to greatly reduce the amount of air being exhausted through that fume hood. It needs to be at a minimum 150 air changes per hour of this volume inside the fume hood. That's about an 85% reduction of exhaust air from when that sash is up, or from when the fume hood is, if it was constant air volume. Now, this is one fume hood. You can imagine a lab that's got a dozen fume hoods in it, and general exhaust and all of that. And if it's all constant air volume, you have a tremendous reduction in the amount of exhaust air coming from that lab. And more importantly, the amount of air, outdoor air, that needs to be heated, cooled, and dehumidified to make up for all that exhaust. And let's dive into the detail a little bit. How do you actually calculate energy savings? Where are they coming from when you make these conversions? Well, this is a exhaust flow analysis table. And to the left column here, you can see there's 3 labs that are identified here, even though they got a funky name to them. These are just 3 labs. And here's the volume for each one of these labs right here. And what you do is you identify each piece of exhaust equipment in the lab, whether it's general exhaust, fume hoods, biosafety cabinets, snorkels, and what their exhaust rate is. Now, this analysis was done for an existing VAV lab that was over 10 years old, so it was still ripe for a retrofit. But you can see they had a minimum valve exhaust and a maximum valve exhaust. So there are already valves there, but they had a minimum and a maximum. In just calculating the air change rate at the minimums, we were still at about 13.6 air change rate in this lab, almost 30 air changes per hour in this lab, which means every 2 minutes you're changing out the air in that lab with 100% outdoor air. And this one was at about 20 air changes per hour. Now, what we do post retrofit is, hey, we want to control these to 6 air changes per hour when they're occupied, 4 air changes per hour when they're unoccupied. So that gives you a different CFM across these 3 labs. And you can see the difference of, even when it's occupied, 11,000 versus 24,000, that's a big difference. And then unoccupied, you get even more gain. Now, you do need to account for the fact that you're going to be working inside these fume hoods a couple hours a day. It's what we use for the industry standard, but the real number is a lot less. So you calculate that in as well, and you come up with your exhaust savings by saying, hey, 2 hours a day, we're going to be using the hoods. The rest of the time, we're going to be at these occupied and unoccupied rates. And in this particular instance, there's about a 22,000 CFM savings of outdoor air annually for just these labs. Now, what we found was, we took this off the valve schedule and we came up with this analysis, but then we used the BMS to trend the exhaust fans and the makeup air units that were serving the labs. And we found that, the actual result was somewhere between these 2 numbers, which one would suspect, it was not varying much, but was still the number we settled in on was around 36,000 CFM of exhaust from those labs. So this savings number actually grew. But it's all about reducing those air change per hour rates in the labs. That's where the energy savings comes from. Whether it's a constant air volume to VAV retrofit, or just a retrofit an existing VAV system, you're always going to calculate those air change rates changes and derive your savings from that. Now, what are the actual components of a CAV to VAV conversion, or a VAV retrofit for that matter? So this diagram here gives us something to talk over talk about what's actually physically involved with retrofitting a lab. Now, down in the left-hand corner here, we've got our fume hoods. And each one of these fume hoods, you either need to add a damper or a venturi valve if it was a constant air volume system, and you need to retrofit that in there and have a controller on there so you control your volume of exhaust to keep your face velocity where it needs to be across your sash opening at a variety of sash heights. Now, if it was an existing VAV system and you're just retrofitting it, well, all these valves are going to be here already. So it's just a matter of retrofitting them with new fast-acting electronic actuators and controlling them to your lower air change per hour rates when the sash is closed. And this is making sure that your face velocities are where they need to be. You know, every lab is going to have some general exhaust as well. If it's a CAV lab, constant air volume lab, you may need to add some general exhaust, but a lot of times it's there already, and you're either going to retrofit new valves into it or dampers and take control of those with new actuators. A lot of the older systems have pneumatics, believe it or not. There's still a lot of pneumatic lab control systems. So replacing those with electronic is always a key. And snorkels, you know, these snorkel exhausts always constant air volume in labs, and they can be a significant increase. So just adding a damper or venturi valve in there and having either an on-off switch or a timer to control that is a great strategy. Now, it's not just about the exhaust. You have a supply air system coming into the lab as well. So we need to get control of that by controlling the existing valve or adding a new one. You're going to have a reheat actuator you're going to want to control as well. And you're going to want to control this supply to maintain proper lab pressurization. So that's a strategy called CFM offset. So from all of these devices, you need to get volumetric feedback to know what all your exhaust is from this lab. And then this comes into what's called a room space controller. It's your brains of your lab. And you have all that volumetric data for the exhaust, and then you control your supply to be a couple hundred CFM less than your total exhaust volume. That's how you control that negative pressure in the lab. That's how you keep the air flowing from the corridor into your lab and maintain that code requirement. And that's also the brains for occupied, unoccupied air change rates. You got a occupancy sensor tied into this controller. When no one's been in there for a period of time, you can reduce your air change rates by reducing your general exhaust, and then your supply would be proportionally reduced, so you keep that CFM offset at a couple hundred. Now, that's what you're doing in the labs. You also have to make sure that your exhaust fan is VAV. So sometimes you need to add a fresh air bleed damper and control that to maintain a constant static pressure in your exhaust plenum. We're going to discuss this a little bit later. And then on the supply side, your makeup air unit needs to have a VFD and a static pressure controller, again, so you're just maintaining constant static pressure in this supply air system. Now I'm going to turn it over to my colleague, Bill, and he's going to take you through some examples of some installations that have been done in the past.
Thanks, Paul. So yes, this is a valve retrofit, and this is basically what we're doing to the lab space with the existing infrastructure. Picture to your left is a Venturi valve, constant volume, and the picture to the right is the after retrofit with an electric actuator. Now, how we basically do that is we end up installing a base plate and the electrical actuator, which then will get wired to a controller. And again, based on sash position, it'll adjust accordingly to ensure that safe conditions exist for that user when in front of the hood. Next. This following example is one of a damper, a very similar situation here. Again, like Paul mentioned, we reuse a lot of the existing infrastructure. So what that does, it helps us, one, cut down on downtime in the lab space, but also makes the conversion very, very quick. Not much of an issue for us to get in and out of a lab with very little effect on the lab users. But you could kind of see here just basically installation of a damper, reusing the existing infrastructure, and then basically taking control of that fume hood or supply or exhaust. Next. My favorite part of coming up with this data is basically the pre and posts. And just kind of to show you here, the chart to the left is hood number 1. The chart to the right is hood number 2. Basically, the orange line on the top part of the chart symbolizes constant volume. In this particular case, 800 CFM, or a 6-foot hood running 24 hours a day, 7 days a week. Once we do the conversion, again, as mentioned previously, we're able to reduce that exhaust by 85% by converting the existing infrastructure. And you can kind of see the blue line going through the left side of the actual usage of that particular hood and what the savings would be for having a VAV system exhausting at 800 CFM versus the VAV system exhausting at about 105 CFM. Industry standard, usually when doing our energy calcs, we call for 2 hours a day where someone will be in front of the hood with their arms inside the fume hood doing experiments or whatever they're doing. Other than that, we're looking at taking advantage of 22 hours out of the day and maximize our savings or our exhaust in this particular case. But you could kind of see here in this particular case, and this is not a rarity, believe it or not, but a lot of these hoods just basically get very little usage. And you'll end up seeing something like this where you just start exhausting 105 CFM versus 800 CFM all the time. Next. So that's basically a little information on the exhaust. Now let's talk about a little bit of the supply. Supply is obviously where the money comes from. That's what's costing us money, is supplying that space. But this is kind of just a before and after of some 16 lab hoods where we converted from constant volume to VAV. All our equipment was installed, and you can kind of see here the supply necessary to feed the existing hoods was about 8,300 CFM. Once we turned on our VAV system and started getting that reduction, we were able to bring that down to 2,800 CFM. So you can see a savings of about 5,400 CFM coming from the supply. In this particular case, in the Northeast Boston area, saving the customer about $65,000 a year in air. Next. Another way of measuring another case study is basically monitoring or trending the supply of VFD and seeing what that VFD does. Kind of self-explanatory on what we're able to do there. Basically, again, pre-VAV system, constant volume, where that VFD was running. And then once we took control of the system and slowed everything down, and you see the post to the right of the red line. Next. One more pre-post case study, tremendous case study at a pharmaceutical in Cambridge, basically where we were able to reduce their exhaust CFM from 45,000 down to about 20,000 CFM. Again, there's two reasons for this. One is we're controlling the airflow, as discussed, where we're reducing that valve 85% when the sash is shut. But we're also reducing the auto sash closer, or I'm sorry, reducing the position of the sash, reducing the position of the sash by our auto sash closer, which we'll get into in a second. Next. As Paul mentioned, there are many aspects to the lab space, and one of them is fume hoods, which is your main driver to your exhaust. However, we do have other items as well. Snorkels, for example. We've been in universities where controlling the snorkels were all about balancing the building, and they were that important. You get a little CFM in every snorkel, and you multiply it times hundreds and hundreds of snorkels in the space. It starts to add up to quite a bit of energy and quite a bit of airflow. In this particular case, we like to set up or install dampers in those snorkels and take some control of them. How we do that is by basically an on-off switch like you see in your screen, or by a timer switch as well, where we discuss with the lab users and put a timer switch for 20 minutes, 30 minutes, 40 minutes, an hour. And basically what'll happen is while they're running their experiment, they turn the snorkel on. And then after a predetermined amount of time, that damper will again close and basically provide savings for that end user. All this data will then get brought over to the room space controller, which will then calculate if the damper is open or not, and whether we need to keep supplying air or we can reduce that supply. Next. Now, all these different items of the lab space are necessary to be able to control, as Paul mentioned, air change rates through our room space controller. So what we're doing here is basically one of these iPad type looking controllers gets mounted on the screen of or on the entrance of the lab, and basically provides you real time, real information on what's happening in your lab space, controlling to either 6 air changes or 8 air changes or 4 air changes unoccupied. And basically what we're doing is we're controlling that to that number, depending whether your snorkels are on or off, or your fume hood sash is lifted or closed, and basically maintaining that optimal level of 6 air changes per hour, regardless of what's happening in that lab space. Next. Finally, the beauty of this particular system is the auto sash closers. And what this does for all of us here, it guarantees our energy savings, and it guarantees that we will be using or maintaining that lab in its optimal capacity. Auto sash closers are essentially what the name refers to, and it basically just auto closes your sash. We are basically taking all these items, installing them on the hood, and ensuring that that sash is closed. We find from our experience that researchers are good at a couple things, and one of them is researching, and the other one is leaving their sash door open. And by having an auto sash closer, we can guarantee that that sash is going to close when someone is not in front of it. Now, these are all the components that basically go into the auto sash closer. For example, we have a sash position sensor, which tells us where that sash is at all points in time. A personnel sensor that will basically detect if anybody's standing in front of the hood or not. An under sash sensor, which basically is a laser beam an IR beam that goes across the bottom of the sash handle, which will prevent the sash from closing on any obstruction that has been left overfilling the fume hood itself. And this basically will guarantee that the fume hood will be as efficient as possible, whether someone is in front of it or not. Next. A quick little video to show you kind of the auto sash in operation. Again, when no one's in front of the hood, the auto sash closer will have a predetermined amount of time, which can be modified to 1 minute, 2 minutes, 5 minutes, whatever your end user wants it to be, and then it'll essentially close. So when the researcher walks away and that predetermined amount of time runs out, that sash will close, basically letting the controller know that we can reduce that airflow by 85% and taking advantage of that reduction as much as possible. Next. Finally, regarding the auto sash closer, this is California Title 24 in the Energy Building Code. And basically, the new code for laboratory spaces, whether new lab spaces or retrofit of existing labs, call for an auto sash closure to get installed on every hood. And the reason for it is this study done by Caltech, basically estimating that an auto sash closer will guarantee or have an annual savings of about $3,400 a year. And you can kind of see that because of how expensive laboratories are to run, how expensive fume hoods are to maintain and feed with the amount of air. So hence, lab or auto sash closers are very, very important, not only one for safety, but two to guarantee the energy savings. One more thing about the auto sash closer, it is a completely standalone project. So if you do see a laboratory space or run into a laboratory space that may have a VAV system, functioning VAV system, auto sash closers are completely independent. They're completely standalone, so they can get mix match with whatever system that's currently out there. We just ensure that that sash door gets closed and that VAV system is working to its optimal capability. Next. And I think back to you, Paul.
Yeah, thank you, Bill. Tim, would you please pull up poll question number 2?
And our poll is closing in 5, 4, 3, 2, 1. And the poll is closing.
Looks almost like 75% of the audience has not done project lab energy conservation project. And about 7% has with sash closers. Very good. Thank you. All right, so Bill took us through energy saving opportunities inside the lab, but what about the lab exhaust fans? What can we do there? Well, I'm back to ANSI Z 9.5. We talked about the actual code requirement. This is the code stated a little bit more in detail. Exhaust stack velocity shall be at least 3,000 feet per minute unless it can be demonstrated that a specific design meets the dilution criteria necessary to reduce the concentration of hazardous materials in the exhaust to safe levels at all potential receptors. Now, until recently, no one was taking advantage of this unless. And now with technology being what it is, there is some things that can be done to get significant energy savings from that exhaust fan. But before we talk about that technology, let's talk about what systems are in place in 99% of the university lab buildings that you would visit. It's something called a fresh air bleed system on your exhaust fans. And this allows you to do variable volume control in a lab while maintaining constant discharge from your stack. So on the left here, again, very simple diagram, but we've got a single fume hood here. It's a VAV fume hood. There's a damper in the exhaust stream, which will be used to control the exhaust volumes. Up here, we've got a fresh air bleed damper on the roof, and we've got the discharge from the stack. Now, in this scenario, when the hood is open, the sash is open, 100% of the air is coming up through the fume hood, past the damper, 100% is going out through the stack, and you're discharged at 3,000 feet per minute. So we've got a closed fresh air bleed damper right here, and we've got our discharge velocity up here. So when you close the sash on a VAV fume hood, now you reduce your exhaust by 85%. This damper in the exhaust duct chokes down. This fresh air bleed damper on the roof opens up and allows 85% of unconditioned outdoor air to join your lab exhaust, and you discharge still 100% of the volume. So your fan is at constant volume, constant speed. Your discharge velocity does not change, but you're taking unconditioned outdoor air in place of the lab exhauster. So you don't have to heat or cool this. So you get a tremendous amount of savings of not having to heat or cool or dehumidify 85% of the air, but you're not getting any energy savings from this fan because there's no VFD on it. You're controlling this to maintain a constant static pressure in the exhaust phlegm. So a fresh air bleed controller controls this, but great for saving heating and cooling energy, not so much for fan energy. Well, recently there's been some solutions in the marketplace that are allowing us to use VFDs on exhaust fans. And it's through active sensing of the exhaust stream from the labs to see if it's volatile or not. So this is how it works. We've got an active sensing system in every riser exhaust plenum in the building. So we're sampling all the exhaust air to see if it's contaminated or if it's clean. And when it's clean, we close that fresh air bleed damper and we enable VFDs, excuse me, VFDs on these exhaust fans so that you slow the fans down and you get that motor savings by use of the VFDs. Now it's continuously sampling the air. And if that air does then get volatile, you get some hazardous chemicals in there, it'll immediately shift over to the fresh air bleed system again. The VFDs go to 100% speed. The bypass dampers go into control to control constant static pressure. And you're now back up to your 3,000 feet per minute discharge velocity. Now, when you think about a university and the labs of any university, a lot of them are teaching labs, and there's not a lot of hazardous chemicals being used. It's more of chemistry 101 and organic chemistry. And there's not a lot of research going on in most labs, unlike pharmaceuticals that can be pretty intense. So when you take that into account, that, hey, maybe there's not such nasty chemicals in the fume hoods, and then think about the fact that, hey, there's general exhaust coming from each one of these labs. It's just pulling lab air. You know, that lab air is clean, or else users wouldn't be able to be in that lab. So the general exhaust source is a pretty clean air, and that's mixing in with your fume hood air, and it's diluting it quite a bit. So the point being, you know, lack of serious chemical use in the universities and this dilution that happens, you're going to be using your VFDs most of the time. So it's a great opportunity there. And, you know, a question that often comes up is, hey, you know, how do you calibrate these to make sure that they're always accurate? You know, most systems, they basically send you new sensors on a periodic basis. Like every 6 months, you'll get a new sensor set and you'll change them out. So you don't have to go calibrate them and do any of that. There's a little cost to that, but the savings definitely make it worth it. You know, there's a collateral benefit to VFDs on a lab exhaust fans as well. You know, 3,000 feet per minute discharge velocity, that's pretty fast and it's pretty loud. Some of these universities are nestled in a residential area and you get noise complaints from the neighbors. I've been on university roofs where they're like, hey, anything you can do about the noise? And this helps. I mean, when you reduce that discharge velocity and you ramp your fans down, you get significant reduction in noise. And that's something that can help sell a project in addition to energy savings, as well as safety. You know, these retrofits add a lot of safety to labs, automatic sash closers, really controlling and knowing what your air change rates are. So, you know, in addition to energy savings, reducing the noise when it comes to this technology, and then just making your lab safer is another way to help you sell your projects. You know, and like the auto sash closers, this technology has been adopted in California in their Title 24 code. So what this really demonstrates is that, hey, this is gaining acceptance across the country, right? It's an option. They're requiring you to do something at the exhaust fans, and this type of system is one of the ones that they recommend. And we're seeing a lot of this happening in Boston as well, and it tends to go from one coast to the other and kind of work its way in. So this isn't bleeding edge technology. It has been out there a while, and it is acceptable, even so much so that it's getting installed as part of a code requirement in California. Just finishing up here, there are a lot of resources out there available for you to do some of your own research in labs. There's a half a dozen here federal sites that you could go to learn a little bit more about it, and great resource for you. And before we go into our Q&A, Tim, would you please pull up poll question number 3?
And our poll is closing in 5, 4, 3, 2, 1, and the poll is closing.
Wow, overwhelmingly think it's a good practice to display air change per hour real time in the lab. It's pretty convincing right there. Excellent, thank you. Well, we'll get into some Q&A here. I think there's some questions.
So we have one that came in right at the very beginning of the webinar, and it says, have you looked at condenser coil clean of lab fridges and freezers to cut energy consumption, since most condensers are clogged and owners rarely do the periodic cleanings needed?
Hey, great question. I'll tackle that one. You know, that's not on the air side as much as it is on the condensing side. And at ECM, we have a group that's called HVAC Armor, and they concentrate on coil cleaning and coating those coils with a aluminum-based coating that adds life expectancy and increases energy efficiency. So, you know, on the lab control side, we're mostly working on air stuff, but we do have offerings to handle the freezer, condensing coils, et cetera.
And a question I think is probably really good for this audience is what's the best way for you to do M&V for these lab retrofits?
Yeah, that is a great question. You know, it's the exhaust fan. You've got an existing lab that has an exhaust rate in it. As we said, the labs are all driven by exhaust. The savings are driven by reducing exhaust. So you baseline your exhaust fan. Where is it operating now? And it's either the fresh air bleed damper, how that's working, or if it's constant air volume, it's pretty easy to baseline because it is what it is. And then post retrofit, you trend the same thing. You're trending your exhaust fan performance. And some people would say it's the air handling unit, you know, the makeup air side, but, you know, a lot of times we find these buildings are really negative. Like they're exhausting more than they're making up through the air handling units, and it's coming into the doors and the cracks. And you know, that air is going to make its way to the air handling units, and you're going to need to heat and cool that. So you're selling yourself a little short if you only look at the air handling unit. So, you know, baseline the exhaust fans, and then post retrofit trend their performance of either the fresh air bleed damper, the VFDs, or all of that. And that's a great way to come up with your savings post retrofit.
We had a couple of questions come in about the control system. What's the process of integrating this with the existing controls? And then a good question also for older systems, can pneumatics be used with this?
We are replacing pneumatics on a regular basis. There's not too many people we run into that want to keep their pneumatics. So it's more about retrofitting them with electronic high-speed actuators. So no, we don't keep pneumatics. I can't think of one instance in my career where we've kept the pneumatics. We're always getting rid of them, and people usually thank us for it. As far as the BAS integration goes, you know, we control the lab space. You'll draw a circle around that lab, and that needs to have one leader and one controller doing that. And then, you know, in our instance, we integrate from that lab to the BAS. So one point of connection to get all the information for everything that's going on in that lab, what the fume hoods are doing, what the general exhaust is doing, what the air change rates are, and you read and write through that single point of connection to both collect data, and then you can change set points, et cetera, et cetera. So it's a single point of connection, the BAS integration, and you let the lab controllers do their thing. And then you've got that little interface where you can direct some set points and collect data to make sure it's showing up on the front end computer.
A question that I had also came in is when you're doing the exhaust sensing system and you put the sensors to determine if there's any volatile compounds, is that a generic sensor that just tests for any volatile compounds, or is there certain chemicals you have to design it for?
Yeah, that's a great question. You know, there's a sensor suite that you get that's very specific to each manufacturer, and there's both generic, you know, kind of a wide net they cast, and then if that, you know, particular labs are doing a certain type of research, there's specific sensors that'll be used. So the shorter answer is that your sensor suite gets designed for your specific application.
Very interesting. And then a question about the sash closure. I think this will probably have to be our last question. It talks about the sash closer. When it closes the sash, does it close it 100% or does it stop shy of fully closed? And then also, can you speak about existing bypass hoods that you retrofit? What do you do with the bypass?
Yeah, so you can program the automatic sash closer to stop wherever you want it to stop. And it may be that you stop it a little short because they're running an experiment and they're running some hoses in and out. Most of the time in these big retrofits, you try to find an alternative route for running those so you can close the sash door. So either under the airfoil or even retrofitting a hole through the side. There's, that's kind of airtight. That's another option. So, it's a twofold answer. Yeah, we can stop the closer a little short, but you're not getting quite all your energy savings. And retrofitting the hoses and other stuff so that you can close it all the way is probably the better practice to go.
So I think what we saw in historic labs was the sashes were left to crack open for that airflow. And what you're saying is modern sash control is to close it all the way and to have a hood that can manage with that.
Yeah, and there's always, even though the sash is closed all the way, there's a gap underneath the airfoil that allows air to flow in. So the sash is closed and it's against the surface, but there's a opening below that to let air pass. And I think there was also a question, Tim, about what do you do with the fresh air bypass, or the bypass on the fume hoods, that is. And basically you blank it off. You just, sheet metal contractor, let's just close it so the bypass is not there anymore.
Well, we've run out of time and you have given a lot of information. Paul and Bill, you've done a great job today. If there's any still questions remaining, their contact information is right on the screen now. Please make sure to reach out to them and ask those questions. I know this has been a great topic. We had a lot of attendees today, and I want to thank everyone for attending and for our presenters for doing a phenomenal job today. Thanks all.
Thank you, everyone.
Thank you.